Hello, everybody. We're not quite ready to start. We just figured we'd go live and say hi. How's everybody doing? We got 115 of you out there online already, which is pretty awesome.
Yeah, man.
Yeah. So hopefully you guys can all see us. A lot of guys have already said hello. Great, great, great. Look at that. Look at that. All righty. Excellent. We got Eric, Joe Finelli's with us, Anthony Rykow, of course, Carlton, Federico. Everybody's coming in. Stanley, how you doing, my man? Good to see you. Glad you're back. All right. Let's see. Oh, everybody's on here. Very good. Very good.
Yes, I did, Ant. I just didn't have a chance to review them yet.
Now, guys, make sure you pay attention to this tune. If you can name that tune in one note, I'll be impressed because it's going to come back and play a major role in the very first part of our presentation tonight. Just so you know.
Mr. Rigo, how you doing tonight? Good to see you. Nelson's hanging with us.
Dave Trotter, how are you, David?
Big D.
And Dave has yet another one of his ascot collection ascots on. Yeah, his ascot has an ascot. There you go.
That's right. That's right.
That's right. You know what? I got an ascot too. Here we go.
That's good.
I've been waiting all week to do that.
You've been waiting for that, aren't you? I hear you. I hear you. Yep.
All righty.
That's us Long Islanders.
Long Islanders, yeah.
That's right.
And we got our new T-shirt. Just came in this week, straight out of quarantine. Oh, yes.
Soon enough.
Soon enough. All right, let's share some screens here and let's get this thing rolling, shall we?
Next Thursday, yeah.
Yeah. All right, people, it's 7 o'clock. Welcome to Takeo After Dark Part 6. Boy, we've been doing this a month and a half now, guys. Thank you so much for being with us through thick, through thin, and through whatever else has been in between. Joining us here on the line here, I've got, of course, co-presenters Rick Mayo and Dave Holdorf. Say hi, everybody.
Hi, everybody.
There you go. Dave, of course, is our Eastern Regional Training Manager. Rick is our Western Regional Training Manager, and I take care of the middle part of the country. And somehow these guys have to, look to me to guidance and leadership. Well, that's how it works. All right. Also, we've got John Messenbrink and Tim Ward from Mechanical Hub. And guys, take it away. You guys made this thing happen. So put out an official Mechanical Hub kind of welcome.
Yeah, thanks, Johnny. Welcome, everybody. Like John said, episode 6. It just gets better and better every week, and we have special guests, every week, and the knowledge is just fantastic. So thanks for joining us, and we're proud to be, partnering with Takeo in Mechanical Hub. We're just moving along here. So thanks, guys.
Yep, and we're about 2 months into this, pretty much 2 months into quarantine, right? Maybe a little bit, maybe not quite that long, but it's been a while. It has most definitely been a while. So it's time for us to jump into part 6 of Takeo After Dark. And the way this is going to work, guys, if this is your first time, just if this is your first time, then bear with me. But what we're going to be doing here, the way this is going to work is we're going to talk, you're going to listen, all right? But if you have a question, on your control panel, and a lot of you already seen this, on your control panel, there's a little cartoon balloon with a question mark. If you click on that, that'll allow you to type in a question. So please type in whatever questions you want throughout the course of the presentation. We'll be taking breaks every so often to address those questions. And as has basically happened over the last 2 weeks that we've been doing this with such a large group, guys have been staying on until till 9:30 Eastern time, basically 2.5 hours after we started. People are still on asking questions, and quite frankly, that's something we enjoy. We love that, man. We love talking. We love talking shop. Basically we're picking up a toolbox, sitting on it, and yakking with you guys about whatever it is you want to yak about. So that's kind of what it's going to work. It's going to work. That's how it's going to work tonight. So any questions you have, and we will all stay on as long as you guys want to. So please, whatever you got. The other thing, again, this is a suggestion. It's easy to zone out sometimes in webinars. So if you have a pad, a paper, and a pen, great. If you don't, go get one. Treat this like a classroom experience. Take your notes, as we go along, just like you would if we were sitting in a class together. Okay, that's the important thing. That'll help you stay focused. It'll help you keep engaged, and it'll help you think a little bit, think through this stuff, and hopefully to make sense. And if it doesn't make sense, it'll lead you to ask a question, which is what we want. All righty then. Let's get rolling here. And let's just talk real quick about last week. We had a great time last week. For those of you who missed it, boy, it was the best one yet, I thought. And hopefully tonight we'll cap that one. But great session. We talked about zoning. It was the ultimate debate. Which is better, zone valves or circulators? And the correct answer was yes. Basically, if I'm sitting in a house, there's no difference. Nobody's going to be able to tell the difference. All right. There's pros and cons to each, and you make the decision based on how important those said pros and cons are. But in terms of delivering BTUs, it doesn't even matter. All right. So we talked about that. We went over some zone valve specific, the TACO 571 heat motor zone valve, the zone sentry zone valve. We went into some depth on both of those, and then we got into some wiring schematics, like we show up there in the upper right hand corner, on how to make different things happen with our zone valve controls. So that was pretty much the big picture of part 5. This week we're going to be we're getting into variable speed circulators, and we're going to do it's a variable speed circulators is pretty much going to be a 2-part extravaganza. Because there's so much there to talk about that we don't want to cram it all into one. Tonight, we're going to focus on ECM myth busting. And there are an awful lot of myths out there about variable speed circulators and what they do. And are they magic or are they not? Did Harry Potter come up with these things at Hogwarts? Who knows, So we're going to be talking about ECM myth busting, separate the fact from the fiction and expose the fiction for what it is. It's in many cases, it's just a fairy tale. And then we're going to start to build the case towards why variable speed circulators make a ton of sense in any system. When we start talking about how they work, what they do, delta T, delta P, and what happens when zone valves close. All right, what happens to system dynamics when zone valves close, and how ECM kind of works with that and helps the system work a little bit better. And then in the bigger picture, how can an ECM circulator help a system be more efficient? So we'll be talking about that both tonight and into next week. So let's get this party started. And I saw this today. Again, this is a quarantine one right here. Groundhog Day has now been classified as a documentary. I don't know about you, but every day seems to be like just the next one or the one before it. So yeah, we're living in a perpetual Groundhog Day, but we have TACO Tuesdays and TACO After Dark to look forward to, right? Every Wednesday night, we look forward to this. We look forward to TACO After Dark. It keeps me sane. I don't know, Dave, Rick, does it keep you sane? It keeps me sane, relatively speaking.
I at least know what day of the week it is.
Well, there you go. There you go.
Otherwise, I get lost. I don't know what day.
Which actually is pretty good because even before the virus, we had issues, right?
Every day's Blur's Day.
Yeah, there you go. There you go. Well, that song from Gene Pitney early on, "The Man Who Shot Liberty Valance," it made me think. This whole topic, folks, made me think about one of my all-time favorite movies. All right, "The Man Who Shot Liberty Valance" from the early '60s. It was a great old John Ford Western with Jimmy Stewart, John Wayne, Lee Marvin. What a great movie. And at the very end, after Jimmy Stewart's been telling the real story of who shot Liberty Valance, because Jimmy Stewart made a life out of being known as the man who shot Liberty Valance, even though he didn't, John Wayne did. He's kind of coming clean on this, and he's telling these newspaper guys. And at the very end, the newspaper editor throws all the notes in the fire and said, "This is the West, sir. When legend becomes fact, print the legend." And that made me think really hard about variable speed circulators, because legend has become fact for many people. We tend to think these things are miracle workers, and they're just pumps. We call them smart pumps. They're not that smart. They're certainly not smarter than you are, and they don't take away the need to know what the heck you're doing, as much as folks tend to want that to happen. So we're gonna get the legend out of here and get back to the fact. Now, some of the legends we've heard, again, Dave and Rick and I have been all over the country talking, and in both countries, US and Canada, talking about variable speed circulators. And one thing we always do is we always ask, who uses variable speed circulators? And then we ask, well, why? What do they do for you? What do you expect? And these are the most common answers that we found. All right, the first one is yeah, that one's obvious. Well, they save energy. What kind of energy? Electrical energy. How much electrical energy? Buttloads. Let's take a look at that. They do save energy. The small ones save small amounts of energy, but you start getting into bigger pumps, it's actually a very different conversation that we're going to have. Yes, they do save energy, but it's important to make sense of that. People think it's going to be life-changing money with little residential circulators. It's not. What the electrical savings does do is, if you're in a non-rebate state, the electrical savings basically offsets whatever additional price you might pay for that circulator within a year, maybe two, depending upon what you pay per kilowatt hour. That's what it does. It's kind of the cherry on top of the ice cream sundae. All right, it's a nice thing. But yes, they do save energy if you properly apply them, meaning if you know what you're doing and if you know how to program and if you understand systems. Now we're going to talk about something else they can do. They can help make a system work more efficiently and effectively over the long term. Now there's the real value. Just don't focus on the electrical savings. That's a microeconomics thing. The macroeconomics thing is how this thing affects the system overall. This one's one of my favorites. They always give me the right flow. Now there's a statement that actually is about 82 to 83% correct. All right, 82 to 83% correct. That statement needs two more words to be 100% correct. Rick, do you know what those two words are?
I do, only because you taught me well.
Yes. What are those two words, Rick?
Almost never.
Almost never. Yes. They always give me the right flow, almost never, right? Or hardly ever works as well. It's not what they do. All right, it's not how they work. They don't know load. They know open, they know closed. All right. Delta T does a better job of inferring load because it's based upon the supply and return water temperature. That'll do a better job of getting you closer to the right flow, but it has limitations on the low end. All right. Delta P only knows pre-programmed operating parameters, and that's pretty much it. It doesn't know how cold it is outside. It doesn't know anything else. So they always give me the right flow, not even close. They'll vary their speed under certain circumstances, but that's not to be confused with giving you the right flow. Here's a thing to note, write this one down. I was discussing this with a guy in Wisconsin at a trade show, and he said, all I know is with a variable speed pump, when a zone valve's closed, the flow changes, the flow goes down. I said, well, that happens with a fixed speed pump too. That's not a news flash. It happens with a fixed speed pump too. A zone valve closes, there's fewer holes, the flow goes down. It's the way it is. Okay, so we got to understand what that means and how that works, and we'll discuss that. And this one just is kind of almost laugh out loud, embarrassingly laughable. Well, they take the thinking out of it. They do the thinking for you. They take the guesswork out of circulator sizing. No, no, and no. They certainly don't take the thinking out of it. And to suggest that they do the thinking for you, to me, is borderline insulting, because that's basically saying, all the years of experience and knowledge and learning that you've invested into your career is basically saying, here, take this pump, none of it matters. If we could get a trained monkey to put it in, we could do that. It is ridiculous. It is a ridiculous statement. They don't take the thinking out of it, and they absolutely don't do the thinking for you. They're not that smart, like I said. A few more, push the button, it'll figure everything out for you. Push that magic button and poof, it does all the work. It's great, it sizes itself, and nothing is further from the truth than that. And then they're magic. Because when someone has to say, well, ask them how it works, well, they're magic. When they say they're magic, that's their way of saying, waving the white flag and saying, I have no idea how they work, and don't ask me any more questions, right? They're magic. They're not magic. They're very simple devices, and they work. There's some incredible intelligence built in there behind the window that we'll never see, that make them do some interesting things. But by and large, what does a variable speed circulator do? Zone valve opens, it goes faster. Zone valve closes, it goes slower. That's about it. All right. It's up to us to make sense of how to apply them appropriately beyond that. So where do these legends come from? I think, as we said, the legends come from just not knowing. You know, you got people trying to sell these things that don't really understand them, or they're trying to appear as there are folks out there that try to appear to be experts and aren't. And when they're asked to explain something, they kind of get lost. And the best they can come up with is magic, or it does this, and kind of panders. And then these legends get repeated and repeated and repeated. And before you know it, that's what everybody thinks. So we're going to put a stop to a lot of that tonight, I hope. And guys, please feel free to share your experiences here with variable speed circulators and what some of the things that you guys have heard as well. So so those are all important things for you guys to do to help get the most out of this program as we possibly can. And I see Rocky Pavey on the line here, and I just washed your mug, man. That heat is on mug. I had it out. I had it on my desk not 15 minutes ago. I went to go fill up my water bottle and I put it in the dishwasher. How about that? It's been sitting there since yesterday morning. So what can I do? All righty. Very good. Very good. Let's take just a quick status check. How's everything going out there? Very good. Hopefully you guys are all doing well. And John, do we have a guest that we'd like to kind of bring on? Is that are we ready for that one yet?
I'm going to check and see. I'm going to unmute his mic and see if we can get him on here real quick. All right. Dan, are you there?
He's also yep, there he goes.
Can you hear me?
Yes, we can.
I'm here.
Is this Dan Foley?
The legend.
The reason we have Dan Foley on the line here, folks, is about 2 weeks ago, Dan was hospitalized with a COVID-19 related virus and pneumonia and was really quite ill. And those of us who love you, Dan, we're very worried and scared for you. But by golly, you pulled through and you got home. What was it like, and how are you feeling now?
Well, actually, it wasn't 2 weeks ago. It's 1 month to the day, and this really it knocked me out for about 3 weeks. But
wow.
I'm climbing back. I'm getting my strength back. This is my first week back to work, working half days. Let me tell you, I got a new respect for the C19 virus because I've never been sick at all, and it knocked me out for 3 solid weeks. But it's good to be back. Good to be on this side of the grass and joining everybody tonight. So thanks for inviting me, John.
No, well, thank you. So glad to have you, and so glad that you're feeling better, and you're going to be with us for a good while. And yeah, we're glad you're on the phone, so we won't get you sick again. But awfully glad to have you here. And this thing came on you really fast, didn't it?
You know, I felt funny one day, but I wasn't sick. And the next day, a little bit worse, and then bam, it hit me. I couldn't move. I mean, I was sleeping 20 hours a day, and did a virtual visit with my doctor, and she went through the symptoms and said, go straight to the ER. Something's not right. And I was tested, and sure enough, was positive. I also had pneumonia, and I was in the hospital for 7 days, but I recovered quickly. And let me tell you something, for what I saw in the hospital, I got off easy. Okay. I didn't have a ventilator. I didn't have the oxygen. I responded quickly to the treatment, and I was out of there in a week. There were people in a lot worse shape than I was, so I consider myself fortunate and lucky.
Well, God bless you, Dan. Thank you for being with us, and I'm so glad that you're healthy, for you and Christy and all the people who care about you. So thanks for joining us tonight. We'll put on a good show for you.
Great. Thanks, John.
Excellent. Good to see you. Good to see you, man.
Take care. All righty. Good guy. Good. One of the very best, and glad that dodged that bullet. My goodness. Wow. That was awful. But, all righty. The show must go on, gents. So with all of those myths and legends out there, and all these things we've been saying they don't do, well, why would you go variable speed? Why would you use a variable speed circulator? I think that's a good question. And in many cases, people look at it and say, why would I use a variable speed circulator? Well, maybe for the reason the same reason that this guy who lives on that island has a car, because he can, right? There's actually more to it than that. There's a lot of really good reasons to use variable speed circulators, but you got to know the right ones from the wrong ones. Now, the best applications for variable speed circulators, of course, are zone valve jobs, obviously. As zone valves close, they slow down. As zone valves open, they speed up. Delta T and delta P do that in different ways with different input, informational input, and we'll talk about that. Now, the question always comes up is, well, what about using them as a zone pump? Would you use a variable speed pump as a zone pump? And just for giggles and grins, while I'm bleeding along, just type in your answer in the question section here. Would you use a variable speed pump as a zone pump? Because the thing is, if you were to use a variable speed pump as a zone pump, some of them aren't going to change their speed, man. You know, a delta P pump, when used as a zone pump, isn't going to change its speed. A delta T pump very well may. The larger the zone, yes, very well may. But a delta P pump is not going to vary its speed when used as a zone pump. And why is that? Well, we got to understand that information that each circulator uses to speed up or slow down. A delta P pump, and that'd be the TACO 0015E3, 007E, 0018E, 0034E, and then all the others out there, the Alpha, the Stratus Eco, and all the other ones out there. They all basically work the same way. They react, what they're trying to do, let's say in constant pressure mode, what they're trying to do is maintain a fixed pressure differential within the system. They're trying to maintain a fixed pressure differential within the system. So let's say I've got all four zones are open, and the pumps pumpulating and the impellers impellerating round and round and round. And there's a certain resistance. There's a certain resistance against that impeller. All right. Now, once a zone valve closes, now all of a sudden that impeller is impellerating against more resistance. There's more resistance, more back pressure, if you will, but it's more resistance. So what it's going to do then at that point is, hey, there's more resistance. Something obviously closed. I better slow down, and so I get back down to that constant pressure setting. And we'll show you this in a slide a little bit later on. Another zone closes, more resistance against the impeller, the circulator slows down. Zones open up, it does exactly the opposite. Zone opens up, less resistance against the impeller. To maintain that constant pressure, it'll speed up. Speeds up and slows down based on the resistance against the impeller. Now, if you use that as a zone valve, if you use that as a zone pump, all right, each zone has its own circulator. There's nothing in that zone that's going to tell that pressure differential to really ever change. It's not going to change. So that circulator is going to go the same speed all the time whenever it comes on. It's a fixed speed circulator, so to speak, in that sense. So does that mean, well, that it's going to be a fixed speed circulator? Why the heck would I use it? Well, the reason is that fixed speed, you might be able to adjust that fixed speed so it is perfectly sized for the job that you have. Let's say if you need 3 gallons a minute at 6 feet ahead, you might be able to set that pump up to do 3 gallons a minute at 6 feet ahead, so we don't overpump under design conditions, and we overpump less under less than design conditions. Huge benefits there. We kind of touched on them last week. All right. So that's one reason. The other reason is that the actual operating point might be, I don't know, 17, 18 watts. It depends, compared to 85 or 95 watts with a fixed speed pump, like a 3-speed pump at contractor no callback mode. So now you kind of have that difference. Now you kind of say, okay, I can do this with 17 watts instead of 85 watts or 95 watts. I can get my operating point closer to where I need it to be. Now you've got some benefits there. Now with a delta T pump is going to be a little bit different. That has a sensor on the supply and on the return, all right? And it's monitoring the temperature difference of the water going out and the water coming back. Okay, it doesn't care what the water temperature is. It doesn't fight with outdoor reset. A lot of people have said that. No, absolutely couldn't care less what the water temperature is. It only cares about the difference between what's going out and what's coming back. Okay, so what we have is the sensors are sensing that temperature. As zone valves close, all right, as zone valves close, what's happening is now all of a sudden we're not taking the load is lower. We're not taking as much energy out of the fluid. All right, that return water temperature at that same pump, at that same speed, is going to the return water temperature is going to start to creep up a little bit, and the delta T is going to get a little narrower. All right, it's going to get a little narrower. So what that pump's going to do then to maintain the prescribed delta T, the delta T that the system was designed for, it's going to slow down. Another zone closes, we're taking less energy out of the fluid, circulator is going to slow down yet again. Zones open, opposite happens. We're pulling more energy out of the fluid. The delta T wants to get wider. We see this with a fixed speed pump anyway. If we have temperature gauges on the supply and return, I don't know why any of this is a surprise. All right. So the pump starts to speed up in order to maintain the prescribed or designed for delta T within the system. And it's eminently logical and incredibly simple. The other thing that it'll do is there's another thing that will cause the load to change in a house, and that's the weather. As it gets colder out, we're pulling more energy out of the fluid to replace the heat that is lost. So that delta T is going to naturally want to get wider. We see this again in systems, in real systems with fixed speed pumps. The pump will speed up and go a little bit faster in those colder weathers. All right. So, and it'll slow down as it gets warmer, just how it works. Okay. Because GPM equals BTUH divided by delta T times 500. If the delta T is fixed, we know the BTUH is going to change. The GPM has to change along with it. It's simple math at that point. So that's kind of how the two of them work. Understand this about a delta P pump. In constant pressure mode, it's going to run the same speed in October as it does in January, as it does in April. A delta T pump is very likely to go faster in October, or faster in January, slower in October, slower in April. All right. So those are the two options, a broad overview on their operation. So now you start to think about applications. Well, zone valves, either one's a duh. A zone pump, yeah, either one's fine too. You might find a little more benefit with a delta T depending upon the size of the zone. The smaller the zone, the less benefit there is, and we'll get into that as well. And then lastly, we have electrical savings. Yes, we are going to save electricity, but what I would like to do is take a few minutes and put some numbers to that. Because again, the conversation very early on was these things were going to save an immense amount of electricity. Why? Because it said so in the brochure. It's going to cut electric bills by 85%. It's going to cut the electrical consumption of the circulator, maybe, potentially by 85%, depending upon how we set it up. But I want to put some numbers to that just so you know and see if these are kind of interesting for you. So let's take a look at that. And before we jump in, Dave and Rick, do we have any questions out there we need to address before we move on?
Let's see.
One of them came in from Christopher Warner, and he was asking about with outdoor reset, when the output temp lowers, how do you prevent the condensing with the program differential? Okay,
if we want to prevent condensing with a cast iron boiler, well, obviously you're going to have a floor on that anyway, right? Of what, 100 and about 150 degrees is probably the lowest that thing's going to go, 155 degrees for supply temperature. If we have it programmed into a 20-degree delta T, which we very well may, we're going to be in a position where 155, the lowest water temperature coming back is 135. Does that approach the condensing point? You think the condensing point might be 127 thereabouts, depending upon your elevation? So, I mean, that's at that point, that'll be a math problem. At what point do we want to make sure that does not happen?
Okay. And of course, that's also when only the boiler's firing at the time too. So if it fires and shuts off, then we're not worried about condensing. So we're just going to extract those BTUs out of it. So that's, as we get further into the details on the delta T circ, you'll see that it's going to be sipping the BTUs out of that boiler as we go through. So if the boiler's off, hey, we're not condensing at that point. We're just going to take the BTUs out of it. So
there you go. Yeah, we've had some instances where with the delta T pump, the actual, because of the boiler's firing differential, the wider the boiler firing differential, which happens with outdoor reset as well, the better off we are, because now we can actually satisfy a call for heat without firing the boiler. Ooh, ain't that cool? Yeah, because the flow rate goes down, we're sipping BTUs out of there. So there's something to think about there. All righty, and here's one from Ron Anastasi. If I use variable speed circulators as zone circs, will that help increasing total system flow when more zones are calling, considering zone circs are in parallel? They're going to be variable speed circs as zone pumps are going to be fixed speed pumps. So what happens there, it's going to happen with a fixed speed pump It's this, it'll be the same net result. It just that you may very well have lower flow rates if you program the delta P circulator appropriately. If that's what you're asking, Ron, let me make sure that that's the right answer there. Okay. All righty. Very good. Very good. Let us continue. I'm going to do the math here about costs, all right, and how much it costs to run circulators. Let's say I've got a five zone system with circulators, 5 007s at about 80 watts a pop. That's 400 watts worth of pumping power. To estimate electrical consumption, all right, to estimate electrical consumption, we divide those watts by 1,000, and that gives us kilowatts. So 400 watts divided by 1,000 is 4/10 of a kilowatt, all right? And then the next thing we have to do is figure out how many hours that thing's going to run. Now, this map comes from AHRI, and it just gives you a rough idea based on years of study of the amount of run hours you're likely to encounter in different geographical areas. Now, this isn't an absolute predictor, okay? This isn't an absolute predictor. It's just a guideline, okay? Some winters might be more, some winters might be less. That's just the way it goes. It's kind of a guideline. And you pick your area of the country where you have your run hours. Now, this isn't heat load. Heat load is different. That's the depth of the heating season. This is more like the breadth of the heating season. So I look let's look at upstate New York. Upstate New York looks like it's in the 2,500 hour range, right up in here, 2,500 hours worth of runtime. So let's use 2,500 hours worth of runtime, meaning the circulators, each circulator we can expect will run about 2,500 hours, more or less. So what we're going to do here is multiply 0.4 kilowatts times 2,500 on hours, and that gives us 1,000 kilowatt hours. Now all you do is multiply by your cost per kilowatt hour. National average is about 11, okay, thereabouts, 11 cents a kilowatt hour. Some areas are higher, some areas are lower. I'm going to go with a slightly high average of 15. If you're higher, you're higher. If you're not, you're not, all right? But 1,000 kilowatt hours times 15 cents a kilowatt hour, that's going to run 150 bucks a year for all 5 circulators. That's not per circulator, that's for all 5. That'll run out to about 30 bucks a circulator over the course of a 7-month heating season, okay? Over the course of a 7-month heating season. Chris Gonzalez asked about what is the average run hour in New Jersey? All right, let's take a look back here. In New Jersey, yeah, you're looking between 2,000 and 2,500 on average, 2,000 to 2,500 on hours over the course of a 7-month heating season, which we'll roughly identify as the beginning of October to the end of April. So about 2,500. So we're here at 150 bucks for 5 circulators. Well, what would happen if we said, you know what? I'm going to go with 1 circulator and 5 zone valves. That ought to cut my electrical consumption. It will. It's going to cut electrical consumption by about 80% because 1 circulator is 80% fewer circulators than 5 circulators. It's very simple math. So 1 007 and 5 zone Sentry zone valves at 1.44 watts each. Now we're talking about 87 watts. And you see where we're going here. Now we're at about 218 kilowatt hours, which is about 80% fewer kilowatt hours than 1,000. All right. So at 218 kilowatt hours times 15 cents a kilowatt hour, now we're down to $32.25 annually. Now $32.25 annually. That's probably about 4.5 bucks a month if we were to average it out, about 4.5 bucks a month. Previously, we were at about 21 bucks a month with 5 circulators. So 21 bucks a month, 4.5 bucks a month. I've saved about 17 bucks a month. All right, I've saved about 17 bucks a month off my electric bill. Not bad, but it's not changing anybody's life either. Okay, you're not gonna. I mean, what can you do with 17 bucks a month? I mean, go to the movies once by yourself, maybe. That's about it. All right. So just understand those are the dollars we're talking about. Now, if we go ECM on top of that, let's say we have a pump that averages maybe 20 watts with 5 zone Sentries, you see where this is landing. Now we're at 68 kilowatt hours. That's down to $10.20 a year. All right. And that's maybe a buck and change a month. All right. Over a 7-month heating season. There's a little buck and change. So really what we have found is in terms of electrical savings, those things might save you about $3 a month. Okay, it's a cheeseburger. All right. So a couple years, depending upon your electrical consumption, a couple years and your cost per kilowatt hour, a couple years, maybe up to 3. It depends on how long it's going to take for the energy savings to offset the additional cost of the circulator. What we tell contractors is, hey, you know what? Your customer's going to pay for this circulator anyway. They're buying this pump anyway. All right. One way or the other, they're paying for this circulator. They're buying it. It's just a matter of whether you give it to them or not. Okay. That's just the reality of the situation. And that's just the electrical consumption. We're not even talking about all the other cool stuff that we're going to get to here in a second. But that's the reality of the electrical consumption. I wrote this in a white paper, gosh, about 10 years ago, and people lost their minds because that's not what they thought. And I said, well, do the math. Okay, it's not, I didn't make this stuff up. This is arithmetic, all right? You know, and basically people came to understand that. Now you get into bigger circulators, this starts to be a completely different story. All right, you get into, you know, 0.5 horsepower, 1 horsepower, or bigger motors. Oh my God, we're having a completely different discussion. But little 1/25 horsepower circulators like the 007 and these small little residential circulators, it's big percentages, but you know, understandable numbers. They're not huge numbers. Alrighty. So again, people who are looking at, you know, Homer wanted to save electricity, but now this isn't quite what we had in mind. I was thinking big bucks and I could take a vacation somewhere, but that's not how it works. Alrighty, so if we think about it, then we start thinking about what's the point? What's the point? And I have a couple of questions about the Taco Gold Zone Valve, the 571. We went over that one last week, Jim, but good question to bring up again. That's about 23 watts. All right, that's a much higher electrical consumption zone valve. So that's about 23 watts. It changes the equations a little bit, but it's a very high power consumption zone valve. Alrighty then. So what's the point then? With all of this, what's the point of variable speed circulators? Well, let's get into that. But first, we have our Taco trivia question. You guys ready for the trivia question, Dave and Rick?
Sure.
All righty.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Our winner last week of the Taco trivia question was Rutledge, Robert Rutledge, or Jeff Rutledge, or John Rutledge.
John Rutledge. John Rutledge last week. Yes.
John Rutledge. Jeff Rutledge used to play quarterback, but John Rutledge, yes, he won last week, and he won some 3 zone valves and a zone valve control. Tonight's prize is a 007E variable speed circulator, your very own 007E variable speed circulator. And tonight's trivia question is as follows. As you all know, Taco is celebrating its 100th anniversary this year. We opened for business in 1920, and we are currently celebrating 100 years in business under a single family ownership, the White family. And the question is, in what city did Taco first open for business? In what city did Taco first open for business? You have until we actually reveal the answer to put in your answer. So type it into the question section when you know it, and type it in, and then we'll take all the right answers and we'll sift through them, and then we'll put them in a little spinny thing, and we'll select a winner for this week's trivia question. So the trivia question is, in what city did Taco first open for business? In what city did Taco first open for business? All righty then. We have any questions we need to tackle out there, guys, before we jump into anything?
Well, now I can't find them since we just filled up with all the answers here.
I should have done that before.
You got to look way up there.
But that's okay. That's all right. Let's see here. Let me scroll back up here, and hopefully I don't lose anything. I don't think we had any.
Here's one from Chuck LeMay. Would the Delta P be self-balancing once it sets up? No. I guess that depends on what you mean by self-balancing, Chuck. One of the other myths that I've often heard is people say, well, I put this valve in. If I have different loop lengths, you know, my zones are all different lengths. If I put in this Delta P pump because it's pressure regulated, you see, it's going to make all that go away. All right, it's going to balance everything out, and I'm going to get the right flow all the time. That is, it's inconceivable that a pump could do that. All right. When it's running at one speed. If I've got 3 zones open and that thing's running and it's running at one speed, and I've got 2 long zones and 1 short zone, where's the flow going? It's going through the short zone, man. It's going to go through the short zone, and as soon as that zone is satisfied, it's going to go through the next shortest zone. That's just the way it works. There's nothing magic in that pump that says, oh, wait a minute, let's check this out. This zone's 200 foot long, this one's 160 foot long, and this one's only 100 foot long. I'll balance those out. It doesn't work that way. The zones and the thermostats do the balancing for you. So
Hey,
if that's what you're asking, Chuck, then that's our take on it. Yes, Rick.
how many times did you see The Princess Bride?
Inconceivable.
That's where you said it.
That's it.
It's inconceivable.
My name is Inigo Montoya. You killed
Yeah.
my father. Prepare to
Prepared to die.
Prepare to die.
I love that movie.
Yes.
Very good. Excellent. Great. Okay. Well, we've got a whole bunch of others in here. Now everybody's kind of giving us answers, so we got to scroll back there. You guys do the scrolling and I'll continue here as we, and just jump on in when you've got a good question, Dave and Rick.
All righty.
All righty. Let's take a look at this. When zone valves close, we got to understand what happens within a system when zone valves close. When zone valves close, it's kind of like a big old traffic merge, okay? You've got, let's say let's look at it this way. Let's say you've got a 4-lane highway, all right? And you have cars filling that 4-lane highway, nose to tail, and everybody's going the posted speed limit. Work with me on this one, okay? Everybody's going the posted speed limit and all the cars are nose to tail. Think about that for a minute. Not only is that is the highest possible cars per minute flow rate, known as CPM. That's the highest possible cars per minute flow rate we could have on that highway at that moment, right? And it's also, because I've got 4 lanes open, it's also the lowest overall resistance to flow, is it not? So it's the highest cars per minute flow rate, and it's the lowest overall resistance to flow. All right. Now let's say in lane number 4, out on the left-hand side, bam, we get a little fender bender for some crazy reason. Now all of a sudden, I don't have 4 lanes of highway, I've got 3 lanes of highway. I still have the same amount of cars on the highway though. Unfortunately, what happens to my cars per minute flow rate? I did have 4 going, now I only got 3. My cars per minute flow rate has to go down. It has to go down, it has no choice, right? And what happens right at that choke point, right at the choke point where traffic has to merge from 4 lanes into 3? Well, what happens there is actually the traffic is going to back up. It's going to back up. Remember those words, back up. Traffic's going to back up at that pinch point where we're merging 4 lanes into 3. And as we're merging 4 lanes into 3, what happens to the driver in each of those cars that's now stuck in traffic? Their blood pressure's going up, man. God, you start getting a little road rage going on. I don't know about you, but I think that's a darn good analogy for a zone valve system. Don't you guys?
Great.
Thank you.
I do like that one, yes.
Your enthusiasm, Rick, has me whelmed, I got to tell you.
I'm telling you.
So all zones calling, it's the same thing, only different. I've got four zones open. The water's going. That's the maximum flow rate I can have through that system and the lowest overall resistance to flow. As zones close, okay, as zones satisfy, I get increasing resistance to flow and my gallons per minute flow rate has to go down because I've got 3 holes instead of 4. Okay, I have 3 holes instead of 4. So I get increasing flow resistance as those, and it's just like 3 or 4 lanes of traffic merging into 1. What does that look like? Well, it's going to look kind of like this. Remember last week we talked about system curves a little bit and showed you how to come up with those with the wheel and everything. Well, a zone valve job has multiple system curves. It has one system curve for every combination of zones that are open at a given point in time that you could possibly imagine. For example, a 3-zone zone valve system, a 3-zone zone valve system has 7 different system curves. Let's count them. Zone 1 on by itself, zone 2 by itself, zone 3 by itself, zone 1 and 2, zone 1 and 3, zones 2 and 3, and zones 1, 2, and 3. That's 7 different system curves. So I've got 7 unique system curves on my plot right there. Okay, 7 different system curves. Now, if we add, let's say I've got a system here. Look down on the lower right-hand corner. My zone valve system requires 3 gallons a minute at 5 feet ahead. All right, little 3-zone system, 7 gallons a minute, 70,000 BTUs. 5 foot ahead is my worst case head loss zone. Let's add a pump to this and see what happens. Let's put a 007 on here, a little Takeo 007 flat curve standard efficiency circulator. All right. Now, you see here, I need, right here is my 7 gallons a minute at 5 foot ahead. So right here is where I want to operate. But as we said before, the system will always work where the system curve intersects the pump curve. So we follow this system curve out, and actually I'm working here at about 9.5 gallons a minute at what looks to be about 8 feet ahead, let's call it. All right, that's where it's working. Now, as a zone closes, flow goes down just like on the highway. And what happens is the system curve backs up the pump curve. We have a new system curve, and that intersection point is going to back up the pump curve. So flow is going to go down. Flow, and another one closes. We go up here. Flow goes down some more. Flow goes down some more. Flow goes down some more. So as zones close, flow goes down. That's with a fixed speed circulator, just like a variable speed that we talked about earlier. And those system curves are backing up the pump curve. So the points of intersection are going back up the pump curve. All right. So in this case, as flow goes down, because I'm intersecting on a pump curve, what happens to the head pressure differential created by the circulator? The head pressure differential created by the circulator goes up. All right, it goes up. Now, a flat curve pump is ideal for zone valve applications. It's the preferred selection for a zone valve application. Why? Because of this. Big changes in flow result in very small changes in the delta P created by the circulator. All right, big changes in flow create very little difference in the pressure differential created by the circulator. All right, flat curve pumps and zone valves go together like cake and ice cream. All right, cake and ice cream's perfect together, right? Peanut butter and jelly, whichever one you choose. All right, so they go together perfectly. Let's try see what happens if we were to use a steep curve pump. And this is, maybe this is your typical 3-speed circulator, again, set to contractor no callback mode, or medium speed or low speed for that matter. It's going to be the same relative dynamic. Okay. Again, we have our different points of intersection, but note, as flow goes down, what happens to the pressure differential? The pressure differential not only goes up, it goes way up. So big changes in flow can result in very large changes in pressure differential created by the circulator. That's not so good. Why? Well, it creates some issues. It can create overpumping. All right, as we will see, as we can see here, we might be overpumping our zones, and we're doing that anyway in most cases. So we have that incredible shrinking delta T. But it also, with those such high pressure differentials, we can create a little velocity noise again with those flow rates. But the biggest concern is what happens when the zone valves close. When zone valves close against this kind of pressure differential up in here, they have a tendency, depending upon what kind you use, they might actually not even close. All right. But in many cases, what you'll have is bang. You'll get water hammer noise. All right. When that zone valve closes, it goes chung. That's the zone valve telling you it's not happy. That's the zone valve telling you you're making me close against too much pressure differential, and I'm going to make your life miserable until you do something about it. Zone valves are vindictive that way. All right. So that's the big difference. That's the big difference. So zone valves and steep curve pumps go together more like, ice cream and sardines. All right. Not very well together, or tuna fish and ice cream or whatever you want. Cake and pesto. Okay, that doesn't go together very well. Both are good, but they don't go together very well. So let me know if that makes sense to you, if that's understandable. Because once we see that, then we got to figure out what to do about it. All right, what should we do about it? So say I have this banging zone valve problem with a steep curve pump. Well, you guys tell me, what do you think the easiest solution is here? Oh, everybody's, people have been doing their research. Okay, everybody's got a new pump. A new pump. Yeah, says Andy. That might be the simplest thing to do. Take out, do the hydronics hokey pokey. You take the wrong pump out, you put the right pump in, you take the wrong pump out, and you shake. Oh, never mind. Do you remember Dave? You have kids. You remember the words to the hokey pokey, right?
You got about that's it. That's all I remember.
Okay, very
good.
Further. Well, yeah, there's a lot of guys are looking at this the right way, I think. There's a lot of things you can do here. The first would be simply stay flat, all right? Take the wrong pump out, put the right pump in. Take the wrong pump out and put in a flat curve, you know? Or use a flat curve pump from the get-go. Why create a problem, right? Why create a problem? And if you have to solve a problem, solve it directly and quickly and certainly. Just take out the wrong pump and put in the right one. All right, because we know the pump is causing the problem. Let's take out the pump and not cause the problem. I know, crazy, right? Who would do that? All right, another solution that people will often say is take a detour, use a pressure differential bypass valve. But what a pressure differential bypass valve does, in essence, is it turns a steep curve pump into a flat curve pump. All right, that's kind of what it does. It's just flattening off that curve turns a steep curve pump into a flat curve pump. And if you're going to turn a steep curve pump into a flat curve pump, why the heck not just use a flat curve pump in the first place? I don't know, crazy talk, right? Crazy talk. Why would you spend more of your customers' money to solve a problem that you just created? Why not just not create the problem in the first place? To me, that's just logical. You know, a lot of people say, well, with zone valves, you gotta put in a pressure differential bypass valve. Yes, if you insist on using the wrong pump, then yes, you do. But it is the price you pay for using the wrong pump. It is a Band-Aid for a self-inflicted wound. Simple as that. I'd say 9 out of every 10 applications I've seen a pressure differential bypass valve installed, it was as a Band-Aid. There are instances where you may need one. It very well may happen, and then it's good to have them. But in most cases that I've seen them installed in the U.S., it's a Band-Aid for a self-inflicted wound. And then lastly, you can adjust and adapt. You can use a chameleon circulator like a variable speed. And again, that solves this problem, but there's so much more that they can do as well. All righty, because the point is, it's still system curves and pump curves. No matter what, no matter the circulator, you cannot get around that we have system curves and we have pump curves, and they rule the day. They rule the day. So we can't really get away from that. We can't get away from that. And let's talk about delta T versus delta P. Here's our delta T circulator, the VT2218. And the reason we call it the 2218 is 22 feet ahead out to 18 gallons a minute. I know, logical, right? Line B is max speed and line A is minimum speed. And pretty much what you have here is this big old green wedge of adjustability, of variability of speed, all right? You have a sensor on the supply, a sensor on the return. If the system was designed for a 20-degree delta T, and most are, set the pump up to maintain a 20-degree delta T. All right, what it's going to do is it actually comes programmed as a 20-degree delta T. So those sensors are going to look for whatever the temperature is here and whatever the temperature is there, and it's going to watch the difference. It doesn't care what the temperatures are. It just cares about the difference. So here's what happens. Let's say I have a system where that zone valve job, 7 gallons a minute at 5 feet ahead. That's what I want. Here's my operating point. And what I'll have is, basically, I will have, where are you there? Boom, boom, boom. I will have that as my maximum speed. All right, that's the maximum, that's the maximum speed that circulator is going to run under design conditions with all zones calling. And that looks like it's about half speed. The 2218 peaks at 59 watts and its minimum is 9 watts. So that looks like we can call it 30 watts maybe as its maximum speed under design conditions. Let's say the smallest zone was 2 gallons a minute at 4 feet ahead, and that's right there. And this is the pump performance curve I'm going to have when one zone is calling, the smallest zone is calling on the coldest day of the year. As zones open, we're going to go faster. As zones close, we're going to go slower. So we're on that coldest day of the year, we're bopping back and forth between these two. The performance curve is going to move to match the load. Let me say that again. The performance curve is going to move to match the load. All right. That's unique among variable speed circulators. Now, as it gets warmer, another dynamic comes in, is this line and all of the others with it move down anyway because the load is getting lower and lower and lower. And at some point, you're going to have a 9-watt fixed speed pump right there. You're going to be working on line A at some point during the winter. All right, at some point during the winter. And it's probably going to be fairly early because at 50% load, if 7 gallons a minute at 5 feet ahead is 100% load, 50% load is going to be about 3.5 gallons a minute at a little over a foot ahead. So that's where we're going to be with all zones calling at 50% load. Ain't going to happen there. It's going to work up here somewhere. And at that point, we no longer have that 20-degree delta T. It's impossible because I have a fixed speed pump now, but it's 9 watts. Think about this. For more than half of the heating season in this application, I'm heating that house with 9 watts worth of pumping power. I know, crazy, right? So we're going to be working along this curve for most of the heating season. The delta T is not going to be 20, but here's the point. It's not going to be 5 either. All right. We're keeping it as wide as we can. We're keeping it as wide as we can. Now with the cast iron boiler, and we're getting close up to 8 o'clock. With a cast iron boiler, what's going to happen here is if you have a nice wide firing differential, think about we're taking 180 degree water out and it's coming back at 160 or thereabouts, or wherever we're at, and you know we're trying to heat that. The first thing that's going to happen is we're going to heat that system because we haven't hit our firing differential yet. We're going to try to heat that system with whatever residual heat we have left in that cast iron boiler. It's only at a point where the average water temperature in that boiler drops to below its firing differential is that boiler actually going to fire. All right. So if you got a boiler with a 10-degree firing differential, all right, it'll go on, and we set 180 as the max. The boiler doesn't fire until the water temperature hits 170 or 175, and it keeps firing until you hit 185. So if we're just taking very small amounts of water out of there, you know, we're not cooling that boiler down quite as much. What you'll see is instances where you satisfy a call for heat without ever firing the boiler, and glorioski, Captain Kilowatt, it doesn't get any better than that, right? So that's kind of where we're at with a delta T pump. Now, what you'll see here is in terms of applicability, the bigger the system, the more variable speededness you're going to have. Now, let's say I have a zone pump that was 3 gallons a minute at 6 feet ahead. All right. So using this as a zone pump, that's where it's going to be running under design conditions. But again, as it gets warmer, it's going to start going slower until I'm left with a 9-watt fixed speed pump. I don't have that 20-degree delta T all the time. It's going to be lower, but again, it's better than it would have been. What you have to decide at that point is the added cost of the VT2218 worth that degree of variable speededness? Or could you find use, let's say, this circulator, all right, the 0015E3, could you use a delta P constant pressure circulator, or 0018E with an adjustable fixed speed to fine tune that as well for less money? It's a matter of value at that point, and you need to make that call. But if we're working up here, it's an obvious value. When you're working down here, you have to make a decision. So, all righty. Any questions out there, boys?
There was one that if we went way back up there, Tim was asking about what we call in our industry as inrush current on ECMs. And there's issues out there in some areas where we don't see it on our zone controls or our switching relays, but these smaller ECMs, right when they first start up for a fraction of a second, have a high inrush current. And a fraction of a second, we're talking maybe milliseconds, right? And most relays don't have any issue whatsoever with that. On occasion, some do, and that's the point I believe he's bringing up. So again, we're looking into it. Again, our product is not having issues with that. Our zone controls or switching relays, we're banging these things on and off all the time, and we're not locking up, we're not welding shut, etc. So I do know of some other relay companies out there and some onboard boiler relays that have had some issues. So again, it's news somewhat, and we're checking into it. I don't have an answer for you right now.
Very good, very good. Yeah, we've been turning these things on and off, you know, right from the get-go, and again, they're pretty robust. So we haven't seen any issues either with the pumps, again, or with relays. So excellent question. Excellent question.
The experience that I've seen in a few areas around me has been, it's not necessarily the relay, it's actually a safety relay for the circuit board itself that doesn't like that inrush current. So that's where we see that happening. The issues of kicking on and off like that. So
very good. All righty. All righty. So let's see what else you guys check for any other questions, and I'm going to show what happens with the 0015E3. Now, the 0015E3 is a constant pressure circulator with 3 settings. If you like 3-speed pumps, you'll like this because it addresses a lot of the shortcomings of your typical 3-speed pump. So right here, I've got a constant pressure, let's go back here, constant pressure setting at 5 foot ahead. That's low. Medium, I have a constant pressure setting at 10 foot ahead. And then high happens to be full speed, fixed speed. All right, high is full speed, fixed speed. Now, this 5 foot ahead constant pressure line and this 10 foot ahead constant pressure line, those are fixed performance curves. There's a million different pump curves built in here, as you'll see in a second. But it doesn't matter what happens, the system will always work. If I pick 5 feet ahead or if I pick 10 foot ahead, the system will always work on that curve right there. It has no choice. If I pick 5 foot ahead, the system will always work on that curve there. It has no choice. So let's take a look at our 7 gallon a minute, 5 foot ahead zone valve job. Well, that just hits it perfect, right? That hits it perfect. And if we were to draw out that system curve, it'd kind of look like that, all right? So perfect. Under design conditions, it needs 7 at 5. I'm giving it 7 at 5. Life is good. We've got a 20-degree delta T and everybody's happy.
Yep.
Now we'll just draw in the other system curves as zones close, all right? We'll just put them in here. As zones close, okay, what's going to happen is this, we're going to work either here or here or here or here. Okay, it's going to work on that performance curve. Now, even if the required flow rate, let's say, is down here at say 3 gallons a minute at a few feet ahead, even though this zone only has that amount of load on it, it can't work there. It has to work up here where the system curve intersects the pump curve. There's no other choice for this thing. Energy in equals energy out. It has to work there. The circulator doesn't work up here, then go down there, and then go back up there. That's what the delta T pump does. This is a delta P pump. All it knows is a valve open and a valve closed. That's it. It's a great pump, does really good stuff, and the price of these things make them very adaptable. I mean, you can really get into them and they're approachable. But this is how they work. Just so you know, this is what they do. All right. Now, and if I had said, you know what, 7 gallons a minute, 5 foot ahead, I'm not really sure. I don't know what to do. I'm going to go medium and be safe. Well, now I'm simply working up here. All right. And I'm at that point, I'm not impacting my delta T very much at all. I need 7. I'm giving it 9. That's almost, almost a third more. My delta T is going to be smaller all across the board. System's going to work. No one's going to freeze to death and blame you. You've done that part of the job, but that's the easy part of the job. The hard part of the job, the part of the job that they pay the professional for, is this part of the job, making sure we optimize the performance of the system as best we can. So yeah, this is going to be easy. Put it in. Let's get the hell out of here. I don't care. But we do have the ability, if we know what we're doing, if we know what we're holding in our hands and why, if our products are purpose chosen, meaning they're selected for a reason. I'm using this pump on this job for a specific reason to accomplish one specific thing. Well, then I have the ability now to basically say, you know what, good enough isn't good enough. Right is good enough. Good enough, nobody's freezing to death. That's for amateurs. I'm a professional. I want this to be the best. I want the system to be as comfortable as possible, and I want the boiler to work as economically as possible for as long as possible. Because short cycling, which is what we're talking about here, short cycling not only it ruins the overall efficiency of the boiler, it lowers the overall efficiency of the boiler. It also wears stuff out, right? It wears stuff out. It wears out parts and pieces and replaceable stuff, moving parts. So now you've got maintenance costs that you have to deal with that basically are, again, are self-inflicted wounds. So the professional knows this, and the professional makes sure he understands what these things do and how they do it. All right. There's no magic here. It's system curves and pump curves. All right. How does that save energy, though, is very interesting. This in this pump curve here, within this operating range, a computer programmer has programmed in a whole bunch of different pump curves. So this pump can run on any one of these curves here. Those are pump curves, but we still have our 10 foot ahead constant pressure performance curve. So this is where the system is actually going to run. Let's say again, we pick 10 gallons, we pick the 10 foot ahead constant pressure line, but I'm at 7 gallons a minute at 5 foot ahead. This is where I want to be. All right, let's follow the system curve up, and here's where it's actually operating, but it's operating on this pump curve. Do you see that? It's operating on that pump curve. And if high speed is 44 watts and minimum speed is 5 watts, this, I don't know, maybe let's call it 32 watts, whatever that might be. Let's call that 32. Now, as a zone closes, okay, we have an entirely new system curve, right? And the way this thing's going to work is interesting. It's almost instantaneous. For like a nanosecond, with this new system curve, the system's actually going to work up here on the same pump curve as it senses that resistance. And then almost immediately, it's going to say, oh, no, I don't want to be up there. I want to be back down here. And it's going to jump down 1, 2, 3, 4, 5 curves, or however many, and it's going to start to run slower. And it's going to look like that. It's going to be that quick. But now I'm working on this pump curve instead of that pump curve. I'm using less energy. Next zone closes, same thing happens. We go up here and we drop right down. Then we go up here and we drop right down. And by the time we're done with one zone calling, I'm working on this pump curve. With all zones calling, I'm up here and I'm bopping back and forth between those two. Now, consider the difference between that and if I had, understood it a little bit better and I picked the 5 foot ahead constant pressure line. Now I'm working way down here and I'm using maybe 8 watts to 13 watts or something like that. So again, understanding the programming, understanding the needs of the system and what you're doing is going to allow you to really fine tune this thing as best you can. Now, the question's got to be out there. Well, what if I don't know the flow and head? What if I can't figure that out? Or I know the flow, I don't know the head. How do I figure all that stuff out? Well, and then how do I program a pump around that? If I'm guessing, we actually have a way of taking some of that guessing away. As long as you know one of the parameters, we can tell you the other one. And that's something we're going to take a look at next week when we look at our 0018E with Bluetooth technology. The app for that actually lets you see what's going on inside that system and allows you to fine tune that delta P circulator about as well as a circulator can be fine tuned. And it's really exciting technology that we're going to share with you next week. All right. You guys ready for the trivia answer?
Yes, sir. Go for it.
All right. So as of right now,
a lot of people answered tonight. So
good.
A lot of people have hung out with us quite often, I'm sure, through a lot of training classes over the years.
I think so. Yeah. We tell this story all the time. So as of right now, no more answers, but the trivia answer is beautiful Elizabeth, New Jersey. Elizabeth, New Jersey, home of the Maple Diner. Okay. Elizabeth, New Jersey was where we first opened doors, and then not long after that moved to Providence, and what was it, 1950 we moved into the facility in Cranston. So and it's been a happy home ever since. So there's your story there for our trivia answer, and we'll be selecting a winner out of all the correct answers over the weekend, and we'll let you know early next week who the lucky winner is.
And Christopher grew up there.
Christopher who?
Gonzalez.
Christopher Gonzalez. All right, Chris. Excellent. In Elizabeth, New Jersey. Do you know a guy named Steve Gritson? I went to college with that guy, and he was from Elizabeth, New Jersey, too. But I don't know where he is now, actually. I think he owns a record store somewhere, but hey, that's neither here nor there. So what's up next week? Next week, we're going to be talking Bluetooth technology. We're going to be talking ECM and Delta T. And if we got some time, we're going to throw in a little bit about buffer tanks and modulating condensing boilers and see how that goes. So I think next week will be our next to last session. Then the week after that, we'll wrap up Take-O After Dark. It'll be 8 sessions, 2 months, and that'll be our final session. And we'll see how we'll see where we go from there. So with that, we might as well start with just opening up. One more thing. We got to go to the stickers. How's the sticker supply, Dave?
Oh, it's going well, man. I'm probably sending about 30, 40 of them out a week. So thank everybody for requesting some of those stickers if you're into that sticker thing. I do have a couple up on the wall behind me here. So I got one from Flintstone. I got also from Zella Plumbing the other day. So you send them on over to me. I'll put them up on the wall behind me here too. And then once we're all out of here, I'm going to be bringing them up to Takeo, and we have these big toolboxes that we use in the training rooms. They'll be adorning the toolboxes up there when we get out of this.
Good.
So.
Oh, very good. We're looking forward to that. We are definitely looking forward to that. So again, contact at Takeo Training on Instagram. Give Dave your mailing address, and we'll get you out some stickers in conjunction or in return for your stickers, so we can put you on our toolbox. So very good, very good.
So V, yes, I sent some out just the other day, so you should be seeing them real soon.
Very good. All righty. So I'm going to end the slideshow, stop sharing my screen, and then we'll get to we'll bring back the boys. All right, there we go. So let's get through some of these questions.
There was one I want to bring up from a while ago when you were talking about the banging zone valves and pressure differential bypass valves, and wondering why you don't, somebody there thought you agreed on it, that you liked using a pressure differential bypass valve.
Yeah.
So
I think
heard that wrong. You heard that wrong.
I think someone's
one
trying
of the comments that came in from somebody else, from Mr. White, had said, well, just put in a 007, darn it.
Yeah, Johnny, you're right. You put in 007. There's a reason, boys and girls, there is a reason that the 007 is the #1 selling wet rotor circulator in North America, and it ain't by a little. Okay, it ain't by a little. It's by a lot, because it fits so many applications. It fits the description of an industry workhorse. Okay. You may run into higher head applications in some radiant jobs where you may need to use it. That's where the 0015 standard efficiency pump comes in. But most applications, zone pumping, zone valves, the 007 is a real good workhorse pump. Let's see, I had a couple questions. Stanley wants to know if I'm leading a thug's life. Are you trying to show us your street cred? Are you talking about my T-shirt, Stanley? It says straight out of quarantine.
Not out of Compton. Yes.
Not out of Compton, but out of quarantine. And maybe I should be after tonight. They should put me back into quarantine. Maybe. I don't know. All righty. Let's take a look. What do we have here? Can you deadhead an ECM double? Oh, sorry. Yeah, you go ahead.
No, go for it.
I mean to jump on you there, man.
So I got one here from Steven. So we'll figure this out one of these days.
You go, Dave. I'm going to have a drink. You go.
All right, I got it. All right. So Steven asks, what happens if one of the zones is wrapped wall to wall with baseboard, then the other zones are sized correctly with the Delta T pump? Will it ramp up to try to satisfy that long zone? So the answer is yes, it is going to, but it's also going to average all the zones, that the temperature drop across all of them. And what's going to happen is if you have it programmed for that 20-degree delta, it's going to be an average of 20. So the long zone might be, say, 25. The short zones might be 15. You get an average of 20. And then the short zones, or the properly sized zones, will satisfy a little sooner. And then the Delta T will slowly start to shrink and get to that 20 if you have that really long zone in the system itself. So excellent question, Stephen. Thank you very much for that.
Yeah, still important to balance.
Always is. Yep.
You have to balance.
Yep. And pumps don't balance for you.
Nope.
Pumps don't balance for you. Absolutely. Absolutely. All right. Can I read the question I was going to read now, Dave?
Sir, yes, sir.
Okay. Can you deadhead an ECM 0015 E3? Zone valve job, all zones off, but pump is still powered. How long will it go, and what does it need in Delta P to start again? How long will it go, and what does it need in Delta P to start again? That second half of that question, Jeff, I'm not sure I understand. The first part of that question, I know you know the answer to that. I know you know the answer to that. You've got, we worry about deadheading because it's bad for big pumps. Little pumps, it's not great. Little fixed speed pumps, it's not great for them, but they can deadhead a little bit without everybody getting all freaked out. All right. We've seen, and you've seen, I know this because you told me, you've seen variable speed pumps deadhead for 2.5 to 3 weeks without a real issue. Not saying that you should deadhead them for 2.5 to 3 weeks. Please don't. But you have, what it's going to happen is if it's, that resistance against the impeller, right? If that the resistance against the impeller, if there's no zones open, there's a lot of resistance against the impeller. That pump's going to slow down to about its minimum speed. So we buy a little bit of protection right there. So I think, how long can you do it? Couldn't tell you, but I know you have that that flexibility.
Yeah, it'll ramp all the way down. What tells it to speed back up again? When the zone valve opens. An ECM circulator is looking at the ability or how much water it can fling, so to speak, when that impeller is spinning. So its zone valve opens up and it's been sitting there spinning at 4 watts at that minimum speed, and then all of a sudden its ability to send more, well, it's gonna send more. So that's how it knows to speed up. As soon as that zone valve opens up, it's just going to go faster for you. So it's the ability of the amount of water that it can fling out of the impeller itself.
And I guess just wants to know, how much of a difference in delta P does it need? Well, it really isn't stopping. Really more or less, it's just moving at that minimum speed. It's still spinning, so it really isn't stopping. So I would imagine just any amount of an open zone is going to say, hey, wait a minute, I gotta, I wherever I was, to keep that pressure, I gotta go a little bit faster. So I wouldn't imagine it would take very much at all. All righty, good. And guys, for those of you who this is your first time on, you can stay on as long as you want. You don't have to stay with us. But like I said, last 2 weeks we stayed on till 9:30. So as long as you guys want to stay on and ask questions, please feel free. No reason to leave if you don't want to. But if you got stuff to do, if you have, like, I don't know, what's commonly referred to as a life, you might want to get to it. Otherwise, we'll hang with y'all. All right.
Yeah, for us, this is our life.
This is our lives, right?
Yeah.
If you deadhead a pump for a while, could you cause cavitation? Cavitation is generally caused by something called net positive suction head or low net positive suction head. I'm not sure we'd have that issue deadheading, perhaps. That wouldn't cause cavitation. Cavitation is a very specific thing, and it sounds like you have marbles in the volute with basically oxygen molecules imploding is what happens, and it can. You get this really nasty noise as it chews the impeller to bits. The good news is that the noise is eventually going to go away, as is the impeller. But so there's good news, bad news there. But with a little wet rotor pump, cavitation's almost non-existent. It's very hard to have happen. If you deadhead a pump for a while, basically you're just not moving fluid. I'm not entirely sure you would automatically develop an air problem. Guys, your thoughts? I'm not seeing it, but.
Yeah, it wouldn't cause an air problem, no.
Nope.
Because it's just basically flashing the steam and then comes back to water again after that. So, and it impinges on the impeller. But really, like you said, it happens more on bigger pumps than it is our smaller ECMs or even 007s for that matter. Yeah.
Right. Okay, very good.
Got a question here from Andy Mickelson. How you doing, Andy? Good to see you, so to speak. Does the speed vary based on actual pressure, or is it calculated based on energy use and torque?
It's amp draw.
You want me to answer?
Imagine this. This is kind of a paraphrased version of what I would normally get into, but imagine that big area of operating range. John showed it to you a couple of times where we have low and we have high and we have everything in between. We have all these circulator curves, little subsequent lesser RPM versions of that. Okay. So say, for instance, we set these circulators up in the lab. We probably did, right? And we were able to plot out all these different working points, all these operating points within, let's say there's 1,000, I'm probably exaggerating, but a whole bunch of operating points. And what that means is we've data logged all of these little areas where the pump is working. Okay, so we're looking at the RPM, we're looking at the wattage, we're looking at the amp draw, we're looking at the discharge pressure, the suction pressure. All this stuff is data logged in there. So that's how we can infer what the GPM is and what the feet of head is. So if that at any point in time on the circulators where we give you head and flow, then you'll that's how we get that information. It's motor data, but it's been data logged into the little computer that's in the pump. That's how we know.
I think that's an answer. Very good. Excellent, Rick. Thank you. Andy, let us know if that answers your question. Very good. Very good. All right, what else do we have in here? Bum, bum, bum. Can you give me an example of why you would use delta P over delta T? It seems to me delta T would be all you need. It's a great question, Michael, and a great point. What you have, people always ask me, is there a specific application for delta T and a specific application for delta P, and which is better? Well, that's too hard of a question to answer. For my simple brain, I look at it like this: it's a matter of degree. I would say in virtually any instance, you're going to find a delta T pump's going to outperform a delta P pump in pretty much every instance. Even continuous circulation in TRVs, they're going to work differently, but they're both going to work effectively. Let's say it's a zone valve job. All right, it's a zone valve job. Bam. Depending upon the size of the job, the difference in performance between delta P and delta T might be this wide, it might be this wide, or it might just be this wide. There may not be much of a difference at all. It depends on the size of the job. All right, we talked about that earlier with that degree of variability between the fastest that pump's going to go and the minimum speed. So I think, it's either this or this or this, and that's just understanding the dynamics of what you're doing is going to help you make that decision. Is that degree of variability, a small degree of variability, worth the additional cost of a delta T pump? And they are more expensive. I mean, we don't get into pricing here, but it's safe to say they are more expensive. All right. So if you're trying to choose between a 0015 E3 and a 00 and a VT2218, it's going to just depend on the size of the job. You may find that, you know what, for that extra money, I get this extra performance. I think I'm okay here. The value is fine. If you're zone pumping, again, you have different ways of thinking there as well. The 0018E is a delta P pump that does give you, it throws a curveball at all of this because we have greater degrees of variability, things that we can do that's going to make that a player in this game that kind of, it's like, okay, yeah, I got a little more variability here, but boy, this makes it easy. I'm going to use that. So I don't know if that answers your question, Michael, but it's a matter of degree. All right, it's a matter of degree. But yeah, there are a lot of people that say, you know what, I only use the delta T pump because it does everything I need, and it's more expensive, but it does what I need. So why bother? It's a better pump, and that's fine too. That absolutely is fine. Okay. Very good, very good. How do you sign up for next week? Asked Russell. I like this guy. He's thinking ahead. Russell, great. You'll be getting, everybody gang, you'll be getting a follow-up email tomorrow from us. It'll give you a little link to download a little certificate of attendance. You get a little smiley face. It'll be nice to put it on the fridge and everybody be proud of you during quarantine. And you'll also get a link to sign up for next week. And we'll also be sending out stuff. Mechanical Hub's newsletter will be sent out with information. We'll send it out. Any Mechanical Hub or our social media, you'll find it next week. Trust me, we'll blanket you with that. So you'll be all there. Hey, Andy DeGraff, Mr. Ping, how you doing, buddy? Andy DeGraff, I was invited to this today. Not sure if I was invited to all the previous ones. Very informative. Great job. Andy, good to see you. How's that ping treating you, man? You still hitting that thing long and straight? I hope so. All right, very good. What else do we have here, guys? What other questions?
So with that being said about Andy here, also for those of you that are not sure, if you want to go back and watch episodes 1 through 5, they are uploaded to Mechanical Hub's YouTube page, and we will also be starting to upload them to the TACO website at the same time, and also our YouTube page. Right. YouTube. So take a look at them there if you want to go back and review any. If you have any questions or any comments or anything like that, please get in contact with one of us. And we've been more than happy to answer any of your questions there.
Very good. All righty. All righty. Let's see what else we got. More questions, and again, like guys, we'll stay on as long as y'all want. That's okay.
All right.
Leading a Thug's Life. No? Yep. Go ahead.
Yeah, no, I got one here from Jordan. Jordan always has some good questions, man. He's been enjoying this and really hacking away on the keyboard at these things. But he says, let's say I have an in-floor zone with high head and 2 other zones with much lower head. If in-floor typically uses a high head pump, but I want to use zone valves for my system design, could I still rely on a flat curve pump to accommodate using zone valves, or would I need to have a separate high head pump for the in-floor? That's a challenge. That's a lot of little things going on in there. Yeah.
Well, that's going to depend a lot on control. I mean, I guess always answer a question with a question. In this case, are all these zones infloor, or is this one zone of infloor and two zones of something else? And are the water temperatures the same? If the water temperatures are different, and you've got a water temperature control separate for the radiant, then yeah, you use a pump for that. That's going to require its own pump. If you're going to mix down for that water temperature, that requires its own circulator. All right. If you're somehow trying to work around this and run the same water temperature through all three, basically you're going to have to figure out what's the highest head. Okay, in this case, that's going to be the infloor. Find out what that head is. Find out what the head is of the other two, and see where you're at. Okay, and you may find that when all three are calling, it may be kind of hard to get a pump that can do that. If it were me, I'd do two pumps, but that's that's just me, and that doesn't make it right. That's what I would do. Or a Delta T pump might do it too. Who knows? We'd have to see. With what the specifics are.
Yeah, my experience is when you start getting to the high head for radiant floor, that's when you're looking at mixing valves.
Mm-hmm.
So, when we, so many times are we designing our systems and we're going with the generic loop lengths, 1/2-inch pipe, no more than 300 feet, things like that, is to accommodate for the mix valve being dropped in there and getting the head higher and still using a standard, say, 3-speed circ. But nowadays, as we're looking at our modulating boilers, we're not looking at mixing valves being added to the system, so the head loss is going to get lower. So take a look at the design. You might be able to change the number of loops in there to, if you had 5 loops in the space, make it 6, drop the loop length, get the lower head so you can get to that one circulator in the system. So there's a lot of different ways you can design that system out to make it work the way you want it to do. I've always said, make radiant fit the project, not the other way around. So
right. Yeah. And if you have the ability to do that, if it's already in, then you got to work backwards from there. But yeah, ideally from the get-go, if you can work around that and design it so you can use that same pump. What's something that Rick was talking about a couple weeks ago, right, Rick?
Yep.
If you're doing the design, you have the ability to design around any aspect you want. If you want to use a specific circulator and make the rest of the system kind of fit that for overall energy consumption and performance, you sure as heck can do that, right?
Make sure the dog's wagging the tail, not the other way around. Jeffrey Voss has got a question here. He says, I do a lot of hotel circulation for hot water. Would the ECM temperature pump be a good solution to move the water in a circ system? Well, let me kind of break that up. Understand, ECM just means a high efficiency circulator. Just a motor is high efficiency. It's ECM. That we get a lot of bonus just by doing that. But Delta T would typically cause you to want to run the pump all the time, so it can kind of move, speed up and slow down, and speed up and slow down based on a fixed Delta T. And that's absolutely been done. We have a product that does that now. It's based on our standard efficiency product, the permanent split capacitor motor, not the ECM. But every way I look at domestic hot water, you don't need to vary the speed of the pump. What makes the most sense when you look at the big picture is you bring the circulator on, you evacuate the cold water out of the lines, you fill the lines with hot water, and you shut the pump back off. That's what you should be doing in domestic hot water recirculation. There's no need to try to use some kind of algorithm that was meant for closed loop heating or cooling applications, or in this case, even Delta T. It has worked and it does work, but the best thing to do is use the right pump, set on the right speed, and turn it on and off as needed.
Amen.
Amen, brother.
Amen.
Can I get an amen for that?
You got an amen for me.
I didn't even ask.
Here's one. But would a Delta T circulator work for a single circuit snowmelt system? Yeah, absolutely. You just set the Delta T to 30. I guess the point is you might be using more pump than there might be more technology than you need there, because think about what you want to do with what do you want to do with a zone valve system? I'm try that again. What do you want to do with a snowmelt system in terms of your pump? Rick, Dave, you guys know this. What are you trying to do? trying to melt
No
snow, right?
fast and furious.
Yeah, you want to
Well-
melt snow fast and for fast. You want to you want to melt snow fast and for furious. Yeah, so slowing the pump down, it's a single circuit and it's a single zone, really, face it. It's not gonna delta P is not gonna vary the speed any. You just want to get that, you just want to pump out there and melt the snow. I think very similar to what Rick, you were just kind of saying about domestic hot water recirculation.
Yeah.
So if setting up, if you're going to use an ECM pump, you can set up that 2218 as a fixed speed pump.
Yep.
All right. It has 4 fixed speeds that you could choose from as well. That would be the mode I would use it in for a snow melt system. Yeah, there's no reason to have it ramp up or down. Just bam and go.
If you're close to the job, try it. See, as long as you can go back and switch it back to fixed speed, but
There you
can
go.
play around. Rocky Pavy's on this call. Rocky's done some cool stuff with that pump. He's actually chilled beer going out and long hoses out to the taps to keep it cold all the way out to the tap. So there's all kinds of stuff we could do with a 2218. So Rocky Pavy, thanks to you for thinking outside the box.
I didn't know that. You need, keeping beer cold in Alaska was all that much of a challenge.
Well, when you're indoors where it's warm.
Well,
absolutely.
yeah, I suppose you could leave it out and that would do it, but yeah,
Right.
That's.
I'm just
All right.
throwing up a picture. There's another opportunity with the Delta T Circulator, and if it's a small enough zone and you can eliminate some mixing and you throw in a heat exchanger on it, I use the Delta T pump in set point mode, and I use it as a mixing control to maintain a set temperature going out. Now the snow melt pump that you see with the radiant manifold there, that would be a fixed speed pump, but now we maintain a fixed temperature going out and kind of work it that way too. So that's another way you can use your Delta T Circulator in a snow melt zone.
Cool.
This is why I bring these two guys to every webinar I do, because they make me look smart, and they know their stuff. I like.
Oh yeah, we learned everything from you, JB.
No. Yeah, these are the guys. They answer the questions. You just watch. I say, well, guys, what do you think? That's me saying, I don't even know, man.
Hey, another
All
plug
right.
to go back and look at other, this is our number 6, right? So there's 5 other ones. One gentleman had a question about, estimating pressure drop on a system, and we covered that in one of the previous sessions, but we kind of need to know what the pipe links are and kind of know what your load is as far as GPM, and there's plenty of ways that we can go in and estimate that. And you can look that up on a mechanical hub, right? They can see these old versions, ones we've already done on Mechanical Hub.
Mechanical Hub's YouTube page. Yeah, John, they're all up on the YouTube page, correct? John Messenbrink, if you're out there. Yeah, and they will be on Taco's YouTube page as well. So you can go back and watch all of those. There's a question that I'm going to ask Rich McGrath to please elaborate on. Are there actually infinite points between the high and low curves, or will it operate on the 3 curves? If you could elaborate on that, Richard, I'm trying to understand what you mean there. So just if you could rephrase that or just elaborate a little bit. What are you trying to get at, so I know what you're talking about?
You might look back, Johnny, and find that the min max with all the subsequent things in there, and I think that might be his answer right there.
The different on the Delta P pump with the different.
Just all the little in between min and max, and that kind of gives you a visual indication.
Right.
You could almost get 40 speeds out of it. Yeah.
Yeah, if you go by watt, yeah.
If you use watt as an increment, yeah.
Yeah, exactly. And next week we're gonna show you some really interesting stuff with the 0018E it's just gonna blow your mind. I think it's a really cool pump that does some pretty interesting stuff. All right, let's see what else we have here.
Nelson had something actually. He was just wanting to bring up if there's any questions about our color coding on the little LED on our little 44 watt platform, and now even the 170 watt platform. So he was just throwing it out there to see if there was any clarification somebody needed on the colors of the little LED. We put a lot of that documentation, a lot of that information in our documentation, so you can refer to that. But if there's any specific questions, I just wanted to acknowledge Nelson threw that out for us. So.
Okay, good. I mean, basically for the standard pumps, we'll leave the 0018E off to the side for it, but the 007E, 0015E3, you guys go through the colors. In normal operating mode, that LED is orange.
Orange.
Okay. And then it'll turn white under what set of circumstances?
Well, two different circumstances.
Airbound.
Dave's doing it for you right now. So
there we
if
go.
it ever, if it sees a locked rotor condition, it'll turn white for a little bit. You might even see a split little bit of red in there as well. And it's going to try to break itself free. On that platform, it tries 100 times in approximately 15 minutes. And if it can't do it, it just simply locks out on air and tells you to come fix me, but don't throw me away.
Right. Dave, why don't you demonstrate?
I'm going to show you guys right here. So I've got a circulator here that I took the casing off. So here you can see the impeller, and I ran some power to it. Got a little switch on the front side here. If I go and kick this thing on, obviously we're airbound. So you're going to see the operation color, and that means it's running. Now, when you see that light flash to white, what I can feel in my hands is a quick drop in speed. That's trying to purge the air that is stuck in the impeller itself, trying to move it out. It's just a quick drop. And it's kind of like when you've got an air bubble stuck on a circulator, you find the closest valve to you and just grab it and try and shimmy it open and close. You're trying to just change that pressure differential in the system. And in the air purge mode, the circulator is going to try and get that out.
Yep.
The second half, I'm going to hold this one with my thumbs to keep it in place so that impeller's not spinning and turn it back on again. So this is the seized mode now. So the light pattern's going to change a little bit. One is going to try to go to the run speed, and then you're going to see a red light and then flash white. There's the red, there's the flash white. And what I can feel in my hands is the shaking back and forth. Now, if I'm quiet, I'm going to hold it up to the microphone so you can hear it. So what you heard there first was the shaking back and forth, and then up to about 5,000 RPM, trying to shake it free because it hasn't spun. Something's keeping it in place. Something's stuck in there. And like Rick was saying, it's going to happen for about 100 times in 20 minutes. You ever see a red light on a circulator, that just means, hey, we couldn't fix what was going on, so come fix me. But I'm not dead. I'm not burnt out. All you need to do is reset the power, and you're back up and running again.
Right. When the red light turns red, the motor actually shuts off. A typical circulator, if it's got a locked rotor, it's on and on and on and on and on. It doesn't know any better. All right. And that's when the pump gets really, really hot. And if you go to a no heat call, if you're lucky, the pump will still be hot when you get there. And you can say, oh, it might be a locked rotor. You whack it with a hammer, you take it apart, you see what the deal is, and try to fix it. If you get there and the pump's cold, then the pump's dead, and you really don't know why. All right, you really don't know why. You're just going to replace it and get them a new one. What this will do is it'll try to unlock itself, and if it can't after 100 cycles, 20 minutes, then power goes. We kill power to the motor, the LED turns red, and as the guy said, come fix me. Very good, very good.
Also,
here's an interesting.
Awesome.
Oh, go ahead. Go ahead.
No, I was just agreeing.
That's so rare.
All right.
I think I want to savor this moment. He's agreeing with me. How about that?
Hey, Mike Hansen has a question about using the 2218. Well, he had one question. He said, scratch it. He said, let's talk about using it as an injection pump for radiant. A couple things about using that for an injection pump for radiant. Remember, it's not a reset control. It's a set point control. So I'll assume you know everything about injection that you should understanding your drops and your pipe spacing and all that stuff. This will work fine as a set point injection controller. So let's say you had a hot loop that was 180 and you had one particular area you just wanted to run the fluid temperature at 100 or 120 or something like that. And every time it comes on, you're going to bring the circulator on. The circulator is going to have now a sensor out on the secondary, and it's going to say, hey, this sensor needs to be 100 degrees. So it's slowly going to ramp itself up to give you that. Now, I will caution you that the 2218 is a pretty good size pump.
Yeah.
So unless you got a big load, that thing's going to stay at 9 watts.
Yeah.
And you're not going to get a lot of float. In fact, you might overshoot depending on how big that load is and how small it is. So
Yeah, you
just
spend
be
a
careful.
lot of money. You spend a lot of money on a pump that doesn't need to do much.
Yeah,
Right? And you really
that'll
can't get
never. Yeah, it'll never come up through the range of the pump's capability. So just be
right.
real careful with that. So.
Yeah, there you go. Well, here's one from Ferris Stanley. If you go in an unoccupied house with a new investor owner, have no history on the heating system, and the system has been open and missing the pump of the loop, how do you determine the size of the pump needed for the system, and how will you determine the direction of the circulator? Okay.
Oof.
That means you get out your calculator and a tape measure and you do a heat loss. I mean, if you're at that point in the system, I mean, if you're at that point in the process, you got time here. All right. We're not talking about this has to be done today. You do a heat loss. All right. You do an analysis of the entire system. Make sure the system, if this guy's looking to buy the house, he just doesn't want this system to work. I would imagine he may want to know, is this going to work? Is this going to work the way it's supposed to? And from there, you just start with, okay, let's identify what I need to have happen. Let's take a look at what we have, and then we can work at it from there. At that point, I would do a heat loss, a room by room heat loss. Figure out where my piping zones go as best we can, and that if there's you just have to take a look at it and see where all these pipes go, and if it's one pump per zone and all the pumps are gone, all right, or if it's one pump and multiple zone valves, well, then you kind of know where it's supposed to go. And that's just one of those things where you got to take 2 steps back, say there's a problem here that I need to solve, but first let me identify the problem. And in this case, the problem isn't that there's no pump there. The problem is I've got an incomplete heating system for a house that is someone's looking to buy. The bigger problem is, how do I make this not my problem? All right. Because if you just put a pump in there, now it's your heating system and you are responsible for stuff you didn't do. All right. So in my opinion is say, all right, here's how we're going to do this. I'm going to do a heat loss for the entire house. And that first thing I'm going to do is make sure that this heating system is adequate for the house, and then figure out what I need to fill in the missing parts. Otherwise, I don't want to touch it because I don't want to own it. And I think that's a reasonable thing to say.
Yep. Correct. Yeah.
This is twice Davis agreed with me inside of 10 minutes. I don't think this has ever happened before.
I've been drinking.
One part of his question was, I'll answer as far as the direction. The pump's not there, and he's asking what direction. Well, there's plenty of information within the mechanical area, including the boiler, where you can figure out which one's supply and which one's return. So again, that's just kind of knowing, mechanical components and where they typically belong in a system. And normally the boiler manufacturers, especially the newer ones, actually have in and out or return and supply, or something like that, and that you could kind of determine that. As long as they haven't cut all the pipe out and you can't see where it hooks up to the boiler, you can make a pretty good determination of which direction that pump goes.
Yeah, the direction is going to be more important on the boiler than it is on the heating system upstairs. That's irrelevant upstairs. And if you're never sure about the direction of a circulator that you have on a job site, because as you know, we always print arrows, we put them right into the casting themselves so you can easily see them in the darkest of basements, right? If you want to know the direction of a circulator, just go ahead and take a look at it. When you see the circulator there, think of it like it is today. And what is today?
Today it's a right-handed circulator.
No, but today is Wednesday. It's Wednesday. It's hump day. Look for the hump. Right? So you look for the hump. I'm looking at the camera over here like you're looking at me, John, too, and you can't see me. So yes, just look for the hump, then the direction of the circulator is going to be in that direction there. So if you're curious, it's always the direction of the hump, that's your inlet, and then that's your discharge out of the circulator. So if that's what you needed to know, then that's another thing. So
very good. All right. Do you recommend stabilizers in your system to protect pumps when pumping glycol? Stabilizers. Are you talking physical stabilizers or something for the fluid? I'm a little.
Fluid.
I would assume for the fluid. Yeah.
For the fluid? Okay, Rick, what do you say?
Again, a good boiler additive, you know, either, I won't mention brands, but there's 3 or 4 of them out there that do a great job. Just talk to the people you're buying that product from. And a lot of the glycol, pre-mixed glycol has inhibitors. You know, it might even have a stabilizer already in it. So check and see what's in there first. Again, good system fluid quality is a good thing. So look into it. We don't sell that product, but we're sure involved in it quite a bit. I would say refer to who you buy that product from and get the right product.
Very good. Excellent. All righty, some more questions here. Let's see. Do you have a design material I can use to size a system? We have, or go back to our very first session, and you, Federico, and again, either on Mechanical Hub's YouTube page or our YouTube page. And we will go through basic heat loss and show you how to do that. It's by no means a comprehensive heat loss presentation, but it'll get you started in that direction. You know, there are you know, if you really want a good book to start with heat loss and system design, the AHRI has the IBR H22 heat loss design guide. You can find that online. I bought mine on Amazon, you know, for like $30, but it's the H22 heat loss design guide, the H20, and you can, again, look on Amazon, you should be able to find it there. And that'll get you going on heat loss. It'll get you going on, you know, pipe sizing and laying out zones and things like that. That'd be probably the best way to get started. And then, you know, from there, you will learn how to calculate flow, how to calculate head, etc. And those are all excellent. It's an excellent guide for that. And then on our website on takecomfort.com, we have what we call Flow Pro U, which is an online learning management system where we have a bunch of different classes that are broken into little chunks, and there's a quiz at the end of each one, and then at the end is a final exam, and if you pass the final exam, you learn the secret handshake and all that fun stuff. But those are good resources as well if those might be able to help you. Antonio Marte asks, where did the name Taco come from? Where did the name Taco come from? Did we go through that already last time? I think we did,
Yep.
didn't we?
Yes, and I sent him an answer.
Oh, okay. Yeah, it's an acronym. There you go, for the Thermal Appliance Company back in 1920. All righty. Does water quality pose a problem for the ECM motor? Depends on the pump. It depends on the pump. You know, with our circulators, with our small ECM circulators, they're equipped with kind of 2 layers of protection. We have, first, as Dave is pointing out there, we have what we call a bio barrier, which is a brass mesh barrier. It's not a filter, it's a barrier. And what that does is when you fill up the system, it's a wet rotor circulator, water enters the rotor area to cool it and lubricate it, and that's where the magnets are. If you've got a lot of magnetic crapola in the water, and you have a permanent magnet on in the circulator, well, you can see where bad things might happen. That's why that brass mesh barrier is important, because brass isn't magnetic. So what that brass barrier is doing is it's basically making the magnet invisible to the magnetic crap on the other side. So the water's coming into the volute of the pump, the impeller's spinning, that black iron oxide or magnetic crud in the system's looking for it says, there's supposed to be a magnet in here, but I just can't feel it. There's nothing for me here. I'll just keep moseying on through the other end of the circulator and go away. Okay, so that's part of what makes it very resistant to magnetic particles and crapola. The other is what Dave showed earlier, that shore start function, where if the rotor ever were to get locked, it's going to try to get unlocked, and it's going to try very aggressively on its own. So from that standpoint, we're not overly concerned about water quality for the circulator's purpose. The rest of the boiler is a different discussion, all right? You know, Rick, you worked for Triangle Tube for many years, and you can speak as authoritatively as anyone out there on the need for water quality for other reasons. Go right ahead, take it away.
Well, just, yeah, the pump's part of the hydronic system, and so is the boiler's heat exchanger. So are all the other components in the system, the zone valves, everything that water's flowing through. So yeah, we want good water quality, and do your research, get it cleaned up, scrub it, clean it, put your inhibitor in there, and have it part of your planned maintenance, and you'll do everybody a favor. So.
Yeah. Again, not necessary for our pumps, but there are boiler manufacturers now that will void warranties on damaged heat exchangers if they can determine, if they can determine that the water was not
Absolutely.
treated properly. And they'll say, yeah, this heat exchanger is cracked, but sorry, it's not under warranty. You didn't treat the water.
They'll absolutely.
There's an uncomfortable conversation.
They'll take a peanut grinder or something that you can cut into the stainless steel heat exchanger, and they'll expose what's called the tube sheet, where the hottest portion of the system is on a typical fire tube exchanger. It could even be the Giannone style tube exchanger. They'll take and they'll cut those right down the middle, and they'll just look on the inside, or they'll look at that tube sheet, and they'll determine, wow, that thing's got, I don't know, 3/4 of an inch of scale on it. Guess what? No warranty. You know, they told you what the parts per million were in the water quality analysis. They told you what the pH needed to be. And if you don't, you can't prove that that's what you put in the boiler, you won't get a warranty. And guess what? Boiler heat exchangers are a lot more money than circulators. So
yeah, and a lot more money than chemicals, than water treatment.
The heat exchanger can be as much as probably 3/4 of the price of the boiler. So that gets people real excited when they have to give that news to the homeowner after a couple of years of service. So.
Yeah, that's a very uncomfortable conversation.
Very uncomfortable.
Yeah, Wheels is ready to send in some pictures of some failed but open heat exchangers. I'd actually love to see those. Send those over along with it. And you got to figure out what cartoon character Dave is next. All right, because you
right.
You came up with the Lorax for Rick, but we need to figure out what Dave is. So
and I'm growing this mustache out, man. I'm going to have it just as big as can be.
There you go. Awesome.
I just can't do the eyebrows. I can't do the eyebrows.
So. We got it. We got it.
Uh-oh. I don't even want to look, do I?
Uncle
I don't know.
Fester.
Uncle Fester from Rich McGrath. Uncle Fester. Yes.
Tag.
All right. Okay.
Just put a light bulb in your mouth. Let's see what happens, Uncle Fester. All right, Uncle Fester and the Lorax.
Okay.
Very good. Very good. All right. Dan Cook, good water quality is good for the system when the system stops because of poor water quality. Please don't call the component companies or the boiler company. Water quality is the key to longevity of the entire system. You've got it, Dan. Absolutely.
Yeah.
Yep. Yeah, there are companies that they have data on how it actually can improve system efficiency. By keeping that heat exchanger clean, and you get much more efficient heat transfer, just like with a cast iron boiler. It's the same thing, only different.
Yeah. It's just that the cast iron boilers changed a lot over the years too. Back in the day, the cast iron boilers had a portion of it that we called the mud drum.
Yeah.
And the mud drum was just this wide open cavity, low pressure drop in there, velocity slowed down, and everything settled out in the bottom of the boiler. All right. It was supposed to do that. Now the boilers are getting smaller. We got less, and we don't have that free space anymore. So a lot of it just stays in suspension and keeps on getting stirred up in there. And every time we touch it too. So that's changed a lot too over the years, especially as we're putting that boiler on the wall compared to, trucking it in and building the house around it.
Right.
Both Bill and Dan are talking about cast iron boilers to the effect that, yes, it's not just the new stainless steel product. It's the old cast iron. Either they take a peanut grinder to it. We, up in Alaska, used to take a big sledgehammer to a section, and we'd break the bottom of that thing open. And if it had, like Dave was just talking, if it had a bunch of muck in it, and the crack was at the bottom of the heat exchanger, well, we've fatigued the metal. We've overheated it, and no warranty. Again, if it's full of mud, the boilers weren't really built to handle that sort of condition, unless it had a certain cavity, as Dave was just talking about. But the ones I used to sell, again, you get the bottom of them full of mud, you would have a premature failure of the metal. So anyway, they're just making points that system quality doesn't matter if it's what it is. We need to clean it up. We need to keep it clean. It should be part of planned maintenance. So.
Yeah. And that's one of the things that I think as an industry we're learning as far as that's concerned with with ModCon boilers, especially the first, the first go around and really up until recently, a lot of folks can say, I'm not treating the water. I don't need to treat the water. I never treated the water before. I'm not treating the water now. And then problems start to arise, and you wind up paying tuition to the school of hard knocks, man.
Yeah.
It's just gonna cost you some money to learn that lesson, and that's okay. Sometimes that's the best way to learn a lesson. It's not the cheapest way, but it is a definite way. And we have to learn, but it's a way of life. If you're putting in a ModCon boiler, it's not just putting in the boiler and skedaddling. I mean, it becomes a way of life, in that you have to check this thing out. You have to monitor, you have to treat the water. Then you may have to treat the water, put some cleaner in it, let it run for a couple of weeks, then come back and drain that out and put in, some protectorant and stuff like that. I mean, it's a process that we hadn't had to do before. So we've got to be able to, incorporate that into the jobs and charge for it accordingly. So people say, well, my customers won't pay for it. Okay. Then are they going to pay for the new heat exchanger in 2 years that's not going to be under warranty? That's, at that point, why are you giving them the option to do it or not? It should be, this is the package. Here you go. It's not really a choice. It's like saying, well, it's like saying, I'm going to charge extra for solder if I'm soldering up a system. Tells you how old I am. It's, I'm going to charge you extra for the solder. Do you want the solder or not? Because if you don't want to pay for the solder, we'll just stick the pipes together and hope for the best. It's really essentially what you're saying. That's a darn good analogy. I got to write that down. That was really good. And I thought of that right here, right now. I guess no one's as impressed as I am. Very good. Okay, thank you.
I wasn't going to write it down for you.
Thank you.
Sorry, sir. I already agreed with you twice tonight, so I'm done.
Yeah, really. If you did it 3 times, I don't think I could handle the prosperity. Why is it not recommended to install the circulator with the electric motor upright? For the example of the 007 circulator. Dave, show what we're talking about here.
All right. So talking about the motor position going in the upwards direction. So
right.
What we don't want to see, like we're showing here in the picture, we always want to see our motor horizontal. All right, whether you're pumping upwards or you're pumping sideways here. So we want to see the motor on the horizontal plane here, and that is mostly for the air purge, getting the air out of the system. And when you have a circulator motor pointing up, Matt, like this here, like you see with the cartridge, here's the impeller pointing down. The top here is our bearing. Now, these are just ceramic bearings on graphite sleeves. And if we get air stuck up here, you're not lubricating and cooling down that top bearing. So that's why we want to see pointing horizontal position with our motors. We don't like to see them up. And, we do say once in a while you can point down. I'm still not a fan of it, because then when they're sitting and collecting any dirt, you could, get everything to get stuck down in the bottom too. So always like to see that motor going in the horizontal position, whether it's the 7 or even the 7Es. So it's just the way that you want to get the long-term ability out of the circulators, then that's what I'm looking at. Yeah.
Yeah, with the 7, we said you can set it up, you can install it with the motor upright, but you must have a fill pressure of at least 20 psi. That's enough pressure to get that cartridge filled all the way. So if it's not up all the way, you're not going to lubricate, you're not going to cool. And then what can actually happen in there is that water can actually flash to steam inside that little cartridge, and it's going to bang like hell. Again, the good news is it's not going to do it for very long. It'll eventually quiet the hell down, but now you've got a dead pump. Yeah. So that's the downside. The good news is the noise will stop. So 20 psi at least, and it's one of those things, if you don't have to, don't mount it that way.
Right. And the other thing about pointing downwards too on a standard 00, not necessarily the ECM wise, but in a standard 00, inside the cartridge, we also have a thrust washer. So thank you, Sean, for reminding me about that. And it's just the way, if you ever grabbed an impeller, it kind of moves a little bit. It's kind of hard for you to see here, but that moves just a hair. And it moves a little bit more in a standard 007 cartridge. And there's a thrust washer on one side, but not the other. And that's to help when it kicks on that initial start of the circulator itself. So we only have it on one side, not the other. So when you have it downwards, then we're going to have other stuff rubbing on each other on the inside.
I should clarify, the higher PSI for the vertical installation was for the old permanent split capacitor circulators, not for the new ECM product. So unless you see it in writing, don't do it.
There you go. There you go. And that answers Nick Hollabon's question. Very good.
Exactly.
All righty, guys. We're down to 102 people still left out there. And we're coming up on 9 o'clock. So again, you guys will stay on as long as you want to. And this is you read, you tickled Mr. Whelan's funny bones about reading the instructions. Who here reads the instructions?
Only when it doesn't work.
Only when it doesn't work. There you go. There you go. Yeah.
We had a question earlier from Chris. Let me find it again. Sorry, I lost it. Let's see, where is it? Chris Gonzalez had asked about radiant cooling in a residential setting. So wondering if we were going to kind of talk about that at all.
Not so much. I mean, other than we can talk about it in broader terms in terms of pumping, but it's not it's not something we do residentially. We have, on the commercial side, they have some design criteria for chilled beams and things like that. Residentially, in terms of radiant cooling, even when we were all three of us were at Wurzbo, when we talked about residential radiant cooling, the thing that we talked about was we can do it and it's wonderful, but you also have to dehumidify. Otherwise, everything gets wet.
Right. Yeah. Residentially, the challenge that we have is that we have windows and doors that open, that homeowners open. When there's more radiant cooling that goes in a commercial application because when you get to the 22nd floor, the windows don't open. There's no outside doors up there. So there's more of a controlled envelope than you do see residentially. Now, do I know people that have done it before? Oh, yeah. All right. And you really got to pay attention to the humidity levels in the homes to make sure that you're not condensing. And what Rick and Rick probably has a little bit more than I have. I think he's worked on a few more projects. I've got like a handful when I did them back in the day. But my experience was always radiant cooling was best as a separate system, put it up in the ceiling. Radiant heating was down in the floor, two separate entities instead of trying to steal from Paul and give to Mary there.
Steal from Paul and give to Mary. All right. That's a Long Island thing.
I can't remember where I heard it from.
Peter, Paul, and Mary, I think is
Yeah, I think that's where it came from. Yeah. Maybe something like that.
I think he was puffing the magic dragon is what I think.
I'm smoking too many light bulbs.
Easy there, Fester.
They just don't stay lit, man.
All right. So again, we're down to 98. That last one drove a few people away.
I see them dropping like flies.
Yeah, dropping like flies. Okay, this is starting to devolve into anarchy. What's going on?
Yes, yes.
All right. A Wheel says Dave is more of a Mr. Clean than an Uncle Fester. Is that true?
We'll take the opinion of everybody out there instead.
I don't know. We'll bring John Messenbrink back in. Dave, John, what do you think? Is Dave more of a Mr. Clean or an Uncle Fester? We got a no from Rich McGrath and a yes from Jason Mangos. Jason's just agreeing.
So that question, John. I think he's a little bit of both.
He's a clean Fester.
Uh-oh.
And there is the Lorax.
Just wait, I'm going to grow that mustache out, baby.
Right, and he speaks for the trees.
Dr. Evil. Oh, I like it, Scott.
Yeah.
I like that one.
Hey, Dave, put your little finger
Dr. Evil. Like
$1 million.
Dr. Evil. Okay. I think Dr. Fester might be better, but that's.
Don't pick at it or it'll fester.
There you go. All righty. And, again, I've never had a really good nickname. A lot of people say that I remind them of George Clooney.
Really?
Just devastatingly handsome, I think is really where that came from. you know, charming, good looking, the whole thing, you know, and that works for me. I'm good. With
Okay. We'll go with that. Being that you hired me, sir. Yes, sir.
Yes, sir. Okay, now we understand. Yes. All right. All right. Clooney or Carlin? Oh no, you want George Carlin? We got a guy online here, Mr. McGrath. It's kind of he's both attitude and everything. There's a little George Carlin thing going on there with Rich McGrath. All right, we love you, Richard. All righty. Well, we're starting to devolve into just coming up with nicknames, so that might be a time. That might be a good time for us to say cut and thank you all for being with us. Again, really do appreciate everybody taking the time to spend with us on this Wednesday night. Guys, your turn. What do you want to say to the remaining folks?
You. Thanks a bunch. Love being part of it.
You know, I think what John had said when we started doing this was looking forward to Wednesday nights. And it's true. I do look forward to it. This is, it's hard to say that this is work. That I just have a lot of fun doing these nights and have a great time with it. So it is a lot of fun. I do enjoy getting ready for Wednesday nights, getting ready for Takeo After Dark. Definitely. Yeah.
It's kind of like Monday Night Football, you know. It's Monday Night Football is Monday night, and this is Wednesday night Takeo, you know. So maybe that's it's kind of the same kind of, we look forward to it and you build up and everything like that. That's really awesome. That's really awesome. All righty, very good, very good. Folks, thank you for everything yet again, and we will see you next Wednesday night on Takeo After Dark. All righty, John. Any last words on your end?
No, I look forward to next week, and thanks again, all three of you guys, just spreading the knowledge. So I appreciate it, and we'll see you next week.
I appreciate you calling it knowledge that we're spreading, John.
Well, the last 10 minutes.
Yeah, the last 10 minutes we were spreading something else. All right.
And John and Messenbrink, thank you for all the work that you guys do in the back of this and putting it all together and making sure that it's just not the three of us talking to each other, because we do this anyway anyhow. So it gets weird when the three of us are talking, doing seminars by ourselves. But no, I really appreciate you organizing a lot of this and putting it together. Definitely.
Absolutely. Thank you. And
really appreciate the partnership. So
yeah.
Thanks.
And as we used to say in Cub Scouts, a round of applause.
Standing O.
Hub and a standing O. There you go. Thank you, John. Really appreciate it. And thank you, everybody. And we will see y'all next week.
Later on.
Later.